right. Hi, I'm Jubi Taneja. I'm from Gimlet Labs, and I'm going to present our work on Tensor Algebra Equivalence checker. This is a joint work with my collaborators, Natalie, Tom, and Zane. The roadmap of my talk is I'll be discussing the rise of automatic generation of AI-based kernels in this whole modern AI infrastructure, why we need that, how we are shifting towards it, and is testing a sufficient criteria to build, trust in these AI-generated kernels. We'll walk through some examples and see why formal verification is needed, and then we'll talk about the actual tool and conclude with some limitations and future work. So let's start with a broader picture. So the idea is there are so many, the AI pipeline has so many stages in it. Like one stage is focused on running this large models on the GPUs, while the others are waiting on the databases, external API calls to finish, or the user inputs and so on, right? So you can see like there are different flavors of different kinds of workloads that are running today. But the problem is the workloads are no more uniform, but the current infrastructure that we have is still largely homogeneous, right? So what happens with this is we end up wasting a lot of infrastructure cost, because on one side there's one stack which is like doing a lot of LLM inference, while the others are like not fully utilizing the hardware at all. So the obvious question is like, if the workloads have become very diverse in nature, diverse in the characteristics, right? Like why can't the platform be diverse today? So this is the exact problem which Gimlet Labs is solving. So the need of the hour is we need to build the heterogeneous AI infrastructure, and in fact, high performance heterogeneous AI infrastructure. Like Mary Hall today already, presented this key theme, like how, we have shifted towards this real heterogeneous AI infrastructure world. And this is the exact problem which Gimlet Labs is also trying to solve. Now, what will happen, like when we have the heterogeneity, even we can go more deeper into this area and see like, okay, if we know the characteristics of our workloads, we can even send off a certain workload and map it to the particular hardware which we can leverage to the best potential in order to save the overall infrastructure cost, make it more energy efficient, power efficient, and so on. So the fundamental block to build these modern heterogeneous AI infrastructure is still that we need highly efficient GPU kernels for different accelerators. So, and the problem is like this requires a lot of GPU expertise, hardware expertise, knowledge of different accelerators, and even the accelerators are just coming in at a very, very rapid pace that it's hard to even know like how we can leverage them to the best potential. Can we always use our best performance engineering principles and so on? So it's a classic problem which everybody is dealing with. So the question becomes like, can we automatically generate these high performance GPU kernels? Yes, the ecosystem is already here and it's exploded, as you can see. We have tons and tons of LLM-based kernel generators, agents existing today which are generating these kernels and so on. So KForge, highlighted here on the very left, is one of the LLM-based kernel generators which we have built in-house at Gimlet Labs. So this is what I used primarily for my work to generate the optimized kernel generations. So now the question is, if this has become such an important mainstream work today, that kernel generation is serving the needs of this high-end and the heterogeneous AI infrastructure, how do we evaluate these kernels? So there are three main criteria. First is we check whether it compiles or not, whether it is fast or not, and third, if it is correct or not. The first two criteria, like if it compiles or if it is fast, are straightforward to measure and to reason about, but correctness gets very, very difficult to reason about. But let's just see, like we saw there's a big ecosystem that exists today, which is building these LLM-based kernel generators. What are they doing today in order to establish this correctness guarantees? So just to list a very few out of those, big list of, names that I just showed you on the previous slide, all of them primarily are, relying on testing and benchmarking today. We did not find as such like any system which is using formal verification of any kind. So the question is, like, if testing and benchmarking has become such a classic way to build that validation and build that, trust in the AI-based kernel generation, can we actually trust testing itself, right? Is testing a sufficient criteria? We want to answer this question now. To answer this, let's just see like few examples, and see, if it really is, good enough and how we can make testing better. Because I'm not saying testing is a bad thing. Testing is great. It has existed and it has evolved and it is evolving. We still need that, but let's just see, how far we can push the bar. So here is a simple problem from kernel bench level 2. You can see that here baseline PyTorch model is performing a sequence of operations like clamp, scale it, clamp it, and then unclamp it by dividing it by the scaling factor. So here scaling factor is nothing but like a model configuration parameter, and the benchmark has happened to set it to a value 2.0. And when we gave this baseline PyTorch model to KForge to generate a Triton candidate optimization, what it did is it just folded and did an algebraic simplification by folding those sequence of operations into a single clamp, and by pre-computing the upper bound, assuming that scaling factor is set to 2.0, right? So when we gave it to the testing framework, it said it is correct, which is true, because how it validated it is, it took that fixed configuration parameters value and said it is true, it is correct, good. But when we gave it to the verifier, right, verifier said this is not true. And when we give it to the verifier, verifier's job is to not validate it for one execution instance, obviously. It always treats the model configuration parameters as symbolic and tries to look for any existing value. If there exists any particular value of that parameter for which you can prove that baseline is not equal to candidate, and it came up with the counter example 0. So you may think like, oh, this is such a simple problem, right? But if you go into the kernel bench, there are a lot of examples that you will find in which such configuration parameters have baked in constant values, and LLMs get confused when they come up with the optimization, the special case it for those particular values. So the problem gets more tricky when you don't have to play with these smaller problems, but when you are in a real production-based kernel scenario, and if you have used AI-based kernel generation frameworks, it's very hard to even identify like what problem would have occurred to cause this kind of a scenario. So let's move on. You may say like, oh, this is such a small problem, right? Like it's a fixed configuration problem, nobody does that. But we can go on and improve the testing by doing sampled configuration, right? Can we make testing better? Let's do it with the sampled configuration approach. So here is another problem where we are doing just a normalization with another configuration parameter called reduction size in this case. And reduction size is now tested with like different set of configuration parameter values like 64, 128, and 256. Now, when the optimized candidate was generated, what optimizations usually happen is it's a classic strength reduction where it replaced a division operation with a multiplication and a pre-computed reciprocal, right? So it can just but the problem in this optimized candidate is that here it silently chose to use some default value for any other configuration which will be tested now to 1/64, right? Now, testing would only focus on 64, 128, 256, all pass, great, but verifier, will result in a counter example, obviously. So this problem was actually, we found in real when we were testing with some block sizes. So there was a kernel where the block size was actually a configurable parameter for us, and it produced a very nice performant kernel, but we found much later that, oh, the block sizes are actually set to 8 or 16, only then that efficient kernel would work in practice. But as soon as we started to change the values of our block sizes, the kernel just started to, show lesser performance, and hence we found the bug. So this is just a simple representation of like how the bug, started to show up in practice. Now, we have done like fixed configuration to sampled configuration. Now let's just try a different technique and see like can we make testing better again. So this time, let's do some input, distribution. So this is a problem where you can see it's a very, very simple and minimal problem where you're just, returning a identity function. But here we wanted to preserve that all the elements stay in their own position. The entire tensor preserves that layout as it is, right? So when we, we performed some optimization, it happened to just do a layout transformation by replacing that original, tensor with a transpose X, right? When we were testing, so testing was limited to this particular scenario, as you can see I have highlighted here, where we created the tensor with xij is set to I plus j, meaning that if you do xji, that will also be set to I plus j, and hence it is showing you the symmetric distribution form of, it's a symmetric distribution here for the entire input tensor. So testing in this scenario would still, pass because it's limited to that. But when you actually you formally verify it, the verification is not limited to reason only for the symmetric distribution case. Rather, it would treat this whole tensor as symbolic and try to reason about it. And it came up with a counter example, where the counter example is simple to read, where it says like, okay, if x02 is set to 3 and all other elements in my tensor are 2, then the baseline is returning xij, but the transposed candidate is returning xji. Now, this layout transformations are very common when we deal with like NCHW or NHWC and so on. But as the complexity of the kernel starts to grow, these transformations are, very greedy kind of optimizations which LLM starts to perform because it has that, whole philosophy of generating high performant kernels. But sometimes, what happens is we end up just losing the entire semantics of the original program itself. So here, when transpose happened, we just lost the entire meaning of the program itself. But the good thing is like verification can catch that bug. Now, let's try to push one more bar because here we were doing like still, a symmetric way of randomly distributing our input and so on. But how about we just do the fuzzing and push for the boundary case scenario in the next example. So here's this another problem where you're seeing that we have the attention operation, but before you apply the softmax, you have the clamp operation. And at the end of the attention, you again clamp the whole output and return the result. Now, this PyTorch model was given to the Kforge, and we asked it to generate a PyTorch optimized candidate, where what it did is very beautifully, it replaced that original inefficient attention with a scaled dot product attention, which is an efficient form of attention. And then it finally applies the clamp, looks great, right? But the problem is it has the only way to know why this was a problem when we tested, obviously, it was showing to us that it is a good, optimized candidate. The problem was the random fuzzing of your input, a lot of times would not touch the boundaries of the clamp operation also, that it can miss out and treat that clamp operation as an identity operation. So clamp of x would become x itself, and hence the LLMs, that the testing may think that, okay, this testing would only prove that this is good. However, verification, reasons about this entire optimization at a semantic level. And the way we found this problem was only when we decomposed the scaled dot product attention to see how is it, implemented mathematically. Then only we were able to catch like, okay, scaled dot product attention does not have any intermediate clamp operation being applied, and hence, these are actually, truly inequivalent cases. So this was also one of the, production scenarios which occurred in a very complex case. But the gist of the story was that the simplified attention was replaced by a scaled dot product attention, along with the clamping boundaries in between and outside. So the question is, can testing alone, build trust? The answer is no. That's why we delved towards designing this tool called Tensor Algebra Equivalence Checker, where what we do is we take the baseline PyTorch model and the candidate model, which can be a pure PyTorch model or it can be a Triton kernel. So K-Forge is not just limited to generating Triton kernels, it can generate different forms of optimized candidates in CUDA and so on, different backends. But for this work, I chose to do it for the Triton. The reason is because we are also dealing with the space of heterogeneous AI infrastructure. So choosing something very upfront so we don't have to do the lowerings later on and find the bugs was the reason. So we take the candidate, we lower it down to the Tensor Algebra DAG IR. Once we have that, we take both the candidates through the second phase, which is a decomposition phase. This is the important phase where what we do is we take all the high-level operations and just decompose them into the primitive math operations. So my intuition was at that time, like we have always learned the formulas of BODMAS, like do the basic math operations. How can we understand these complicated machine learning operations also in that similar way? So this was intuition being applied in the decomposition layer. Now once the operations are all decomposed, we go further and do the scalarization, because solvers cannot reason about tensors, they can only reason arbitrarily about each element, so we scalarize that. And finally, we take it through the Z3 SMT solver, and we have 3 possible outcomes from there. Whether it has found a bug, then it will return SAT. If no, then it will say unsat, that means the problem is equivalent. And a lot of times it would also return unknown for timeout or resource out and different reasons. So we'll take that same missing clamp example and take that running example to understand the idea. So the first phase extracts this Tensor Algebra IR. For that example, you can see you have the intermediate clamp and the outside clamp. You can just pay attention to that. What I want to show is how decomposition work. You have decomposition rules that are implementing the actual semantics of every operation. For example, here clamp gets reduced to the min of max of and so on, right? And the softmax gets reduced to this whole complex operation, which is division and exponent divided by the multiplication and so on. So what we do is we just plug in those, replace those clamp with the decomposed rule, and we replace the softmax with a decomposed primitive math rule over here. And finally, when we enter into the scalarization, as I mentioned, we have to reason in scalars, not in tensors. So here what you're seeing is the matmul operation got replaced with a mul operation, but it has a reduction access added to it with the summation operation, right? So this is what happens in the scalarization operation, scalarization phase. And finally, I want to also point the attention, since I showed you we have the reduction access coming into picture. You may think how do you reason about these large sizes of tensors, because tensors are generally very large, right? 4K by 4K or 8K by 8K and so on, right? So what we do is we do bounded verification. What it means is originally, I'm taking a different example here, which is a matrix vector dot product. The idea is originally if you have say 256 dot product terms to reason about a single yi, now what we do is if we cap the summation bound to say 2 or 4 because we want Z3 to reason about it well in time, so we cut the product terms. So the idea is it can still reason about the semantic, it can still reason about the semantic of the optimized candidate that it has found. We are not reasoning about the numerical precision of that particular result. But yes, if the bug exists for any conditional access and so on, we will miss that for sure. The another caveat is why we chose to do the verification at a high level, as I said before, was because we are generating the candidates at a PyTorch and a Triton kernel level, so we want to catch this bug very, very upfront rather than doing it at a much later layer. And we still have a lot of engineering challenges. It's a very, very early on work so far. But the conclusion is as we are seeing that AI-based kernel generation has become such a mainstream problem today. So the future is not going to be more about the generation, because generation is still becoming more solvable, and the future lies in building that trust in those, kernel generations that we will do using AI. So yeah, that's all. And we are hiring. If you are interested, please come and talk. Thank you.
Questions at the end of this session. We'll go next.